Okay, hi everyone, welcome back to the channel. Today we're going to be having a look at Centralized A star, C A star. So this is one of the most fundamental and most intuitive MAPF algorithms that we can have a look at, but it's really important as a stepping stone in our journey, because what we're actually going to be seeing is that even though this makes the most sense, it's going to be this centralized controller, as we'll talk about. Well, it actually does not scale at all, right? This is a really intuitive approach, and understanding why Centralized A star essentially fails and really struggles the moment we introduce large problems, well, that is going to be fundamental in terms of understanding how and why we then design algorithms to do different things in the state of the art, right? And I think part of this discussion really is just showing you now, we're starting to see the scale of MAPF problems and why they are actually such a difficult and interesting problem to tackle. So let's get started then. Centralized A star is, well, it's an extremely easy concept. When we start looking at these MAPF algorithms to solve multi-agent problems, well, you can start to see that there's going to be two different overall approaches. So there's first the idea of distributed computing, distributed search, where essentially all of the agents, right, Agent 1 and Agent 2, they're just planned completely independently via some other strategy. So this was kind of like prioritized planning, which we saw in last video. It just means that each agent they are acting in their own interests. They have the information available to them. Sure, there may be these ideas of like information sharing and whatnot in these advanced concepts, but realistically, distributed computing just means, hey, why do I keep saying? But realistically, right, distributed MAPF really just means that you're solving each agent independently, separately, apart. Now, the other idea then is a centralized controller, entering into the idea of Centralized A star. So centralized approaches just means that the agents are treated as if we were some overseeing global controller, okay? So in these kind of problems, we have full information. We can see the entire grid. We can see the location of all of the agents and their status. And essentially, right, we have some overseer that is controlling the system and issuing orders to all of the robots together. We'll actually start to see that this has strong advantages because, as we just saw in prioritized planning, it's a really nice and easy strategy. It actually seems to work in practice well enough. But its drawbacks, right, is because it's not centralized, there are problems it just cannot solve, okay? So Centralized A star is actually going to be complete and optimal, which is really exciting. So that's kind of the strength of the centralized approaches. You need this overseer controller in order to actually make sure that agents can compromise, right, and work together. There's some global viewpoint that knows that sometimes one agent's going to have to delay so that another can succeed. Now, within the centralized framework, though, I do kind of want to note there's like another two subsets. So we have, well, so I wrote down distributed, I wrote down centralized. Essentially, within centralized controllers, we still have either a coupled or decoupled approach, okay? So a coupled approach is what we're going to be seeing here, where it's complete joint space planning, okay? So we're planning all of the agents together in a shared state space, okay? So we plan them fully together. There is the other idea that even in a centralized controller, right, where you can see everything and you can see all the agents, you can then still kind of weave in the distributed approach. And so this becomes decoupled planning. So even with a centralized controller, you're just choosing which agent kind of goes when and things like this, and then you'll issue down orders and the agents can kind of plan themselves or try to get their own version of a path that they like. So there's still like interplay that we can do here. I just want to clarify, Centralized A star is really fully coupled and centralized controlling. We are going to search for, over the entire state space, as we'll see, for both Agent 1 and Agent 2 at the same time. So let's write that down then. So over here in the joint space planning, right, this is what we're doing. Well, let's talk about this. So we are going to treat each agent as one large agent, I guess, right? We're going to be treating all agents together as one being, as one state, with many degrees of freedom. Okay, so I mean that maybe is a little confusing, but we're just kind of saying like we're actually reframing the problem to ourselves to say, hey, this is the problem I've been given. This is my state, this entire board state with agent 1, the yellow agent beginning at C2, and the pink agent beginning at B3. Well, our state, as we're going to see, is going to be those two locations together, and our group agent, our problem essentially, has many degrees of freedom because we can make each agent take its own actions. The degrees of freedom in this sense because you have, it's a kind of like what actions do you have available to you in the environment, and that is simply just the actual number of moves each agent can individually make. Of course, right, collisions are still an issue. This is a massive recurring issue with MAPF. This is what makes the problem hard. And we are going to show that we will, of course, not generate valid states when two agents try to occupy the same space at the same time. So to begin then, let's actually draw up, right, what the state space is going to look like. So while we're doing search, we're going to, our very first state is going to have two agents. So you have agent 1, and agent 1 is at location C2, okay? And in terms of those degrees of freedom, well, we'll see. In standard 4 connected grid maps, I'm just going to use a 4 connected problem. You can do 5 things technically, because in MAPF and time-based problems, right, you can always just have the agent wait at the same location. So we have a bunch of things. You can go up, right, so this will be C1. You can go right to D2. You can go down to C3. You can go left to C2. No, B2. Yeah, sorry. And then you can also, of course, wait still at the same location, C2. So this is all available to this agent. The state space is not over yet. This is all still within one state. We also have the same information then for the second agent who begins at B2. So they have also 5 things they can do, the last one being waiting, but they can also go up. So that's, oh, whoops, so this is B3, B3. So they can go up to B2. They can go right to C3, they can go down to B4, and they can go left to A3. I'm struggling here apparently. Okay, anyway, all of this is to say that this little thing here, this is one entire state. Okay, I'm going to draw these squares around it to show you this is a state. Now, that is a large amount of information. Realistically, the state is actually just C2 and B3. You don't have to, I'm just showing visually, right, that these will be the degrees of freedom available to this state, because I'm going to run out of space very quickly to draw this up. So let's see how this goes. There's going to be a lot of arcs that come out of this, right, as all of these actions, because the degrees of freedom isn't just simply going to be 5 plus 5, okay? If you reason about this, we have to join over the entire joint space, every permutation, every combination of these actions that the two agents, or right, when there's going to be more agents, we're going to see that's going to be problematic, that they can take. So I'm going to draw up a few, right? So I'm just going to draw some ... lines. We'll see how this goes, but there's going to be a lot of ... dots because I won't draw up the full space. What I do want to do then is look at essentially, so the very first state, if I was going to permute through all of these nice and easily here, well, of course, it'll be, hey, this yellow agent moves to C1, okay? And then the pink agents will be moving to B2. Okay, so this is a state exactly as we would expect it. And see now how I'm not bothering to draw out the things. I just thought it'd be useful to draw at the beginning to kind of get used to and visually see how we're going to progress the problem. We would then do C1 and then C3. I'm just going to do a ... here to continue for now. And I'll draw up like certain things that maybe just convinces us of the full size of this first layer, right? We're only at the very first layer in the search tree. And after this, we're going to then talk and draw up essentially what the branching factor is of the problem, what the depth of the problem is, and what the overall describe, I guess in generic terms, the size of the search tree, and discuss how that really shows that centralized A star, even though its default approach, is very challenging. So now to continue the example, we'll have done a bunch of different permutations, and at some point, hey, maybe this agent is now looking at its moves to C3, okay? So just to show you that this would continue, and you will iterate through them, so I'll draw them here. So again, maybe B2, and then maybe C3 afterwards. So what we get then, right, this is still C3. This is just showing you that you would permute through all possible combinations. These are two more states that exist. I'm going to do another big dot, 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 dot. And then what we finally arrive at is just the idea that at some point in time, the last states here, I've kind of run out of space on the board, but the last state then would be, right, C2 and B3. But yeah, so you're going to see that like the combinations, as we start to think about that, it's not going to be 5 plus 5. Well, there are 5 options available to each agent, and you have to look at every combination. Well, there's going to be 5 squared. There's already 25 possible states that you can generate just from our initial location. That's a lot, right? Think about how simple this problem is. There's 2 agents in a very standard 4 connected grid map as well. This is only 4 connected. So things are starting to look a bit weird. Now, for the observant among you, right? Well, actually, I generated the state here, C3, C3. Well, we know, of course, that when the 2 agents go to this location here, of course, that is a conflict. So what that means is, no, we would go to generate the state. We would recognize that, of course, it has an agent conflict, and so we're not going to generate it at all. We will prune this from the search space, which is expected. But note that really we were not able to prune too much. There's still 24 of these states. Or maybe there'll be 23, right? Because there'll also be a conflict when they're both at B2. It doesn't matter. We're printing this from the search space, and this is going to continue downwards for some long amount of time until we're able to actually find a solution. So let's have a look at, of course, this is a very easy problem for us human beings, right? We can solve this in seconds, and the computer has to do a lot more reasoning to prove this. So we have that both of the agents are only 4 steps away from their respective goals. Despite the fact that it's only 4 steps, the very first one is, of course, a conflict. What that means is one of the agents is going to have to wait. So we as human beings can see very easily the optimal solution here will be either one of the agents waits, right, because they have the same distance. So one of the agents will have a cost of 5, one of the agents will have a cost of 4. So thereafter, I think it makes sense then to jump across and let's actually try to reason over then the size of this tree and how large it can be. In terms of, we're going to describe it, not in terms of the numbers I've been saying explicitly, like, oh, there were 5 actions available, things like this. We're going to talk about it in terms of the general terms, a branching factor and a depth. The depth will be the depth of the solution. How far down the tree do we actually have to search before we find the goal and we get to terminate? Now, then I'm going to come back and rewrite all of this in terms of the size, right, of the search tree itself. And the search tree is kind of like the interesting one that we want to have a look at. So let's get to that then. So we're going to have to define a few terms first off, and we'll kind of see how this works. So I think first I'll start with the depth, okay? The depth is pretty easy. How far down this tree do I actually have to go? Well, in this problem it's kind of easy to see. We'll have to have, it's whatever like the last time step was really, right? So in this case, because one of the agents had a time step 4 before it got to its goal, the last one arrived at time step 5, okay? So if we reason over that, I think it's pretty intuitive to see that would be 5 time steps downwards. Instead, what I'm going to do is just define this in terms of a k. So time step of finding the solution, right? So I think that makes intuitive sense. Now, I'll write that over here, right? So let's describe the depth in some terms of k. You could also just call this D, I guess. D equals K in this situation, but we'll see why this comes into play. Now the branching factor is the interesting one. We've started to reason over this. In the first node, there's trivially 1, okay? In the next one, we had 5 squared. There were 5 actions available to each agent. You have to look at every combination. That's 5 to the power of 2 because there were 2 agents. In the third layer, each one of these 25 states, and right, we're reasoning over this in the general term. We're ignoring the fact that small numbers of these will be pruned, right? In the general sense, the worst case, right, if the agents were further away, you would have to generate up to 25, right, in this layer. So when all of the moves are available to you, here, each one of these 25 is also going to have another 25 actions available to itself. So the growth factor is kind of the same. We're going to see that it would be actually, this time, 25 squared. Okay, so can we try to reason over this for a little bit? So it's 1, and then it's, I'll write pluses just because we're going to get to that in the search tree. Then there's 5 squared. Then there's, it seems like 5 squared, right? Because it's like 25 squared again, and so forth. So let's try to define this. I'm going to write the branching factor again. I'm going to use the b, so it'll be like b prime equals something, something, something. I want to define b in this case to be actually the number of actions available to each agent in the environment. So here, right, in this situation, you could have 4 cardinal direction moves as well as a waiting action. So b would be 5. B is the branching factor of an individual agent, and then I'll describe the branching factor as a whole using this term. Now, what's something we also care about, though, is actually describing this not in terms of this simple 2-agent problem, but in terms of any number of agents, right? So I'll use n to be equal to the number of agents, okay? So let's reason over this. In that first layer, it's 5 squared because we know each of the 2 agents were able to do 5 things, right? What that means is that this little squared term here, if we start drawing parentheses, I think things start to make sense. This is actually going to be the number of agents. The individual base term here, in the very first layer, b squared, well, if you had 3 agents, it's going to be b cubed, right? So essentially, we're just saying that the branching factor is going to be b to the power of n. Every time you have b things available to you, and you're having to look at the combinations of all n agents. I think that makes sense. Now, let's start drawing out the search tree that corresponds to this in the general sense. Whenever we do this, I think it's always a little weird, right? Like the first term's a little cheeky because it's always 1. There's always 1 initial state. Well, that's always just going to be usually something to the power of 0 is kind of where that comes in like a nice geometric series terminology. So we're going to have b to the n to the 0 here, because that's 1. And then we see that the next one, right, is just b squared. Well, I'm going to write it as to the power of 1, which makes sense. The next term would be bn squared, right? But dot, dot, dot in our geometric series. Now, what's the last term here? Okay, so we have bn to the power of what? Well, now we have to reason over how many times did we have to go down. The very last term, the very last layer, is going to be, of course, related to our depth, k. So hopefully the size of the search tree makes sense. But we kind of want to reason, and I'm also doing this now because in the next video we're going to look at operator decomposition, which is a slightly different way to represent the search space. And we'll compare the two, and there'll be interesting results. But for now, this is kind of showing you, like, look how large this is growing very, very quickly. I'll draw up like the math here of essentially, right, like if we defined a geometric series, the formula just ends up being this. So bn to the k plus 1 minus 1, the whole thing divided by bn minus 1. Okay? You could just look up the geometric series formula. It's pretty standard. Now, the hand-wavy part here is that usually we're more concerned, right, in the kind of like this big O complexity, this very, very simplified view of the actual growth, like the worst case growth factor. So if we look at all of these terms, what it kind of means is, first off, the -1 is obviously just completely irrelevant, right? This is a constant factor. It's completely blown out. It has no impact on the overall size of the tree. But this division by b to the n -1, well, we're also considering this essentially a constant factor. The number of agents usually won't grow beyond too many. Essentially, this term as well, in relation to the depth of the tree and the size of its growth, is unimportant. So the hand wavy part is just saying, I'm going to very, very loosely then, I'm just going to write this as b to the n to the k plus 1. Okay? That's not too important, but we'll kind of see how this comes into play when we compare it to operator decomposition. This is really the very like hand wavy, this is the general size of the tree. So the last thing I want to do is show you how bad this can be, right? Let's use real numbers, look at the size and growth of these factors, and you'll learn very quickly that certain types of problems are going to very quickly escape us as we enter into kind of like computational complexity of like heat death of the universe, things like that. Essentially saying that we will never apply centralized A star to specific kinds of problems. So give me 1 second. Okay, so I've drawn up over here the branching factor growth of the problem. We're going to describe this not even in terms of the full tree size, because that's already massive. I just want to like, I think it's very simple and more intuitive to see as a human being. Even just for literally the number of nodes in like the first layer of the tree, right? You're going to see how large these grow very, very quickly. And I think that really shows you that this is difficult. So let's start with, we have 2 agents. 2 agents sounds very easy. So what that means is, because we have our branching factor of b to the n, well, this is b squared, of course. So 5 squared. Okay, that's 25. Starting off strong. Then we're going to have 3 agents, which is 5 cubed. I'm going to start showing just some discretized ones. We'll jump to 5, and then we'll jump to 10, just to kind of show you how this progresses. So of course, 5 to the 5, and then also 5 to the 10, okay? So let's look at how the numbers grow. So first, 25, easy, okay? Next, 125 is also fine. Now, 3,125 is, well, okay, we would describe this as like acceptable. 25 is fine. We can kind of solve the problem. It's whatever. It is growing quickly, right, as we just saw, but that's okay. I'm going to say, though, that 125 at every single, like that's the first layer. There's already 125 nodes. 125 is about to be squared and then cubed and then ... This is already challenging, okay? So even with 3 agents for a completely easy, simple grid problem, this is only 4 connected. Well, it's already starting to become challenging. Now, when we get to this, when we get to 3,125 as our base branching factor, that is already, it's just unreasonable. We're already approaching like the limitations of actually being able to solve these problems. And when we get to here, 10 agents is crazy. 10 agents is 9,765,625 for one. That is the number of nodes in the very first layer of the search tree. This is not happening. Using this centralized approach, right, the difficulty is because we have so many degrees of freedom, and you're kind of tackling this MAPF problem in we'll see that it's kind of a naive way, but it's extremely intuitive, right? This is, we would often not expect, you go, okay, I want to model this problem. Oh, I know that I should have a centralized controller. This is the most intuitive way to do it. Surely it'll work. Surely computers are meant to be fast, right? But we're already starting to see the difficulty of MAPF and the size of the problems. Well, we can't solve that. That's not even solved. Now, of course, in the real world, right, you don't just have 10 agents, right? Like oftentimes you have 100. even 1,000 plus, right? So the Amazon robotic warehouses, for example, have, I think, a little over 1,000 agents, robots whizzing around on the floor, and they need to coordinate with each other and plan paths that are obviously collision-free. So real-world problems, it's completely normal for them to have hundreds of drones, thousands of robots, things like this. And we're already seeing that Centralized A star as a foundational approach, it just can't deal with that. And so that's interesting in its own right. But yeah, so this is, I think it's fundamental to understand Centralized A star, because this is such a foundational way to look at the problem. And we're going to develop these ideas further in the more advanced algorithms we're going to have a look at. The very last thing I would want to kind of point you towards is there is a way to make Centralized A star substantially better through this idea of, because we're doing so many surplus node generations throughout this process, well, using something called partial expansion is actually a very powerful way to kind of retrieve some form of feasibility for these approaches. Partial expansion is kind of called PE A star, so partial expansion A star. This is a very interesting algorithm that kind of is applying these partial expansion ideas. It's a very prevalent idea that can be applied to a bunch of different algorithms. This is something I'll also look at in a future video. That will be over in my standard heuristic search series. So anyway, thanks for watching, but the story here is not done. In the next video, we're going to look at operator decomposition, which is a reframing of these ideas. We're going to see that the search tree remains the same, but we're actually going to gain some small advantages just through reframing the way we look at the problem. And then finally, we'll kind of start to see that in the next videos thereafter, there are ways that we need to use a centralized controller. We know that we need agents to coordinate effectively. Well, there's going to be very different ways that we're going to tackle the MAPF problem. So stick with me and see you in the next video. Thanks.